Hey, in this video, I just kind of want to walk through some of the basics of titration and relate it to buffers and just remind you of some of the basics, the concepts behind titrations, and I wanted to get you thinking about what's in the solution in a titration at all points. Alright, so first of all, when we have a titration, we're taking volume of titrant added as the independent variable, and then the dependent variable is pH, because the pH will depend on how much of the excess reactant that you currently have. The most important point on a titration curve is the equivalence point. The equivalence point is when you should have the appropriate volume so that your moles of titrant, could be an acid, could be a base, equals the moles of your analyte. So it's not really about your molarities matching up, it's about the moles that you have. And we can use the curve to come down and get the equivalence volume that then becomes very, very useful and important to us. So now, when you're dealing with the titration curve, remember the titration curve itself really doesn't have much to do with equilibrium. I'm not going to say it has nothing to do with equilibrium, but a titration curve is not really an equilibrium thing. It's a stoichiometry thing. So when you're fooling around with volumes and pHs and things like that on the titration curve, you really are working with the strong acid, strong base, or weak acid, strong base equation. So let's imagine this one I have on the drawing here is acetic acid, so C2H3O2, and let's just say it's a sodium hydroxide curve, or a titrant. So we'll get sodium acetate and water. So anything having to do with equivalence, the half titration point, anything else having to do with an acid and base amount, this is the equation you would use. Okay? Now, on the front side of the equivalence point, this is a very important we especially if it's a weak acid, because if this is a weak acid, or if we did the opposite and we were titrating a weak base with a strong acid, this is called the buffer zone. And I mean literally this entire area essentially is the buffer zone. And what that means is that during the course of your titration, when you're executing the titration equation, you are creating a conjugate to the weak species that you are titrating. And as long as you have a little bit of your original acid or base, in this case it's an acid, and then you have some of your conjugate, in any proportion that is technically a buffer. But we've learned that the second most important point kind of on a titration curve, this is kind of a subjective thing I just said, and it could be the initial, so to me as an AP teacher it's pretty important, is the half titration. So you should remember that. It's literally half the volume, and you can get it from the curve. Okay, it's in relation to this midpoint on the vertical section. That's how we get the equivalence volume. The half titration is literally half that. And this is important because this is when the pH will equal the pKa of your weak species. And it would work for bases too. Obviously the curve would look different. It would start high and go low. And then the pOH would, or the pH would equal the pKb, that kind of stuff. But this is a very important point. So from there, I want to talk about what species are present at any point along your titration curve. This becomes very important. So obviously our analyte in this is going to be a weak acid. We're using the acetic acid example here. So at the beginning, well, before I even go through all that, Since our analyte is weak, we're going to have to be using equilibrium to explain its pH because it does not dissociate 100%. So only because we are dealing with a weak electrolyte do we even have to consider equilibrium. If this were HCl and NaOH, both were strong, this titration is strictly a stoichiometry problem. That's it. That's all it is. But only because the analyte is weak are we going to have equilibrium. And so we're going to have to deal with the dissociation equation for this weak analyte. It's the hydrolysis reaction. And most of us during class this year usually just wrote it as a dissociation. And you would use this never for stoic, you only use this for pH. So after you use stoichiometry to figure out your limiting and excess, then you come back to this and do a Rice chart to figure out your pH. So at the beginning of your reaction, this is where I want to talk about what you have initially. Since it's a weak acid, you have a lot of the molecule. And I'm just going to underline the one we have the most of. Now it is weak, so it will partially dissociate to give me a little bit of H positive and a little bit of acetate. So you have all three things in solution. You also have some water, but I'm not going to write that down. It's not what we're talking about here. So as we go to the half titration point, what do we have in solution? Well, at this point, the amount of our original acid has decreased. We're still going to have some whole molecules here, but the concentration's gone down. But it will still dissociate to give me H positive, and it will dissociate to still give me the acetate. Now, outside of the dissociation of this weak acid that I have less of than I used to, I have made some more acetate through my regular acid-base reaction. So this is going to contribute to that. So at the half titration point, you're going to have equal amounts of the two. That means half of your original acid has made an equal amount of your base, your conjugate. And then by the time we get to equivalence, we've actually used up all of the acid, okay, and we have the equal moles of this, so you've converted all of your acid into the conjugate. So the conjugate is your most common species, and it has its own hydrolysis reaction. I should have saved some more room for it, but I'll squeeze it in here. It's going to react with water. This is also in equilibrium. It's going to remake the acetic acid and give you hydroxide. So we're going to have a lot of this, and because it's a weak base, it's not going to do this to a large extent, but you will have some hydroxide, and you will have some HC2H3O2 from the dissociation or the hydrolysis reaction of the conjugate base. And so if we go back up here, and we'll just put the most common species at each point in titration. So here, HC2H3O2 is the most common. Here, it's going to be the acetate ion. Here, they are equal. And what about the points in between? Well, the acetic acid is constantly on the way down. Just think about this in common sense terms. You're going from all to none, kind of following this pattern, while your acetate is on the rise. It's going from 0 to all. So if you are before the half titration, any point before, your acetic acid I'm just going to put HA here, will be greater than the concentration of your conjugate base. Past the buffer zone, the concentration of your conjugate base will be greater than the concentration of your original acid in this case. So that's very important to know what you have in there. And also, what about your hydrogen? How is it being affected by all this stoichiometry? Let's go back to the half titration point down here. I said at the half titration we have acetic acid, and we've got some conjugate, and that conjugate was added from the stoichiometry. Well, according to Le Chatelier, if I'm adding more of this right here, then what I'm doing is I'm affecting the dissociation of the original acid. So I actually get less dissociation of the hydrogen ion than I would have normally. And your hydrogen ion, as we can plainly see from the pH here, the concentration of your H is decreasing from here to here. And that's purely a function of pH. So let's just say this is a pH of 2. That's a giant duh. We may not have to see this here. So this is going to be a high concentration of H positive, and this is going to be a lower concentration of H positive. So it's always in solution until you get to this neutralization point, which is when you essentially don't have any more. So finally, in terms of limiting an excess, at the equivalence point, your acid and base, again, this works if we did a base and an acid, they're going to be equal. Two limiting reactants when you're at equivalence. If you're before equivalence, your limiting reactant is going to be the titrant, and your excess will be the acid. Past equivalence, the roles flip. The titrant becomes the excess, and your original acid is now limiting. And past the equivalence, if your titrant is strong, you can quit worrying about equilibrium, and you can just go to finding the concentration of your strong electrolyte, which in this case would be sodium hydroxide. So last thing before I end this video is what do we do with buffers? How does this relate to buffers? Well, as I said before, this entire area is a buffer zone. And so you're creating a buffer. So when you're creating a buffer and you're adding something to it, all that means is that you're just going to have to do some quick stoichiometry using essentially, well, it depends on if you have a pre-made buffer or not. But if you add an acid or base to your buffer, you're just going to have to do similar to a titration. Find your stoichiometry reaction, your acid base. Do your stoichiometry first. Always stoichiometry first, whether it's a buffer or a titration. Always stoichiometry first. Find that limiting and excess reactant, and then once you've got the excess figured out, now you can come back and say, okay, what's excess? How much of it do I have? And work your equilibrium from there. And it will be equilibrium because you can't have a buffer unless it's weak. You have a weak species and a salt of its conjugate. All right, so I hope that was a decent review of the concepts here between acid-base, titration, the buffer zone, all those big points. In subsequent videos, we'll do a few examples and kind of talk you through it.